Now, questions related to magnetism. Still, we almost finished like 30% of magnetism. There are topics related to force and applications of electromagnetic induction we will do next week. Now, the question related to the topic which we discussed. Figure 10.1 and 10.2 shows two views of vertical wire carrying the current up through a horizontal card. So the current is going up through a horizontal card. Point P and Q are marked on the card. So there are 2 points which are marked P and Q. On a figure 10.2, means on this figure, draw a complete magnetic field lines through P and indicate the direction with an arrow. So how we will draw this, or how we will show the magnetic field line? So if this is the current is going up, so when the current is going up, like example, this is a paper and the current is pointing up. So if we look from the top, so what it appear, if you look from the top, it will appear it is coming out of the paper. So what you have to do, you have to draw for figure 10.2, you have to use a right hand grip rule. So according to right hand grip rule, your thumb will point in the direction of current. For figure 10.1, how the field lines will be, the thumb will point up and fingers will turn around it. So this will be the magnetic field pattern. But we don't have to draw for one, we have to draw for two. So when we have to draw for the second one, the first two field lines should be closer and the third one will be away. And what is the direction? For direction, right hand grip rule, your thumb should point outwards, and when your fingers will turn, the direction in which your fingers rotate, that is the direction of the magnetic field. So this is how the magnetic field pattern will appear. Because we have to draw a complete magnetic field lines or line of forces through P and indicate the direction with an arrow. And draw an arrow through Q to indicate the direction of a compass. Like if we place a compass needle, at point Q, where it will point? Which one is the right answer? You can use the screen annotation to take which one is the right answer when we place a compass at Q. The magnetic field lines, if I draw the magnetic field lines, this is how your magnetic field lines are there. So the question is, if we place a compass, where the compass needle will point, so compass needle will point in the same manner. So it will point towards the left side. So this is of 3 marks. 1 mark is for drawing the field lines, and the second mark is showing the position of the compass needle when a compass is placed at position Q. State the effect on the direction in which a compass Q point increasing the current. If I increase the current, like example, first I was passing 2 ampere, then I'm passing 5 ampere, will affect the direction of the magnetic field. If I am passing a greater amount of current, will there be a change in the compass needle deflection or direction in which it is pointing? So there will be no change or no effect. Why? Because the direction of the magnetic field depends on direction in which we are passing a current. It does not depend on how much current is passing. So even I pass 2 ampere, I pass 5 ampere, I pass 10 ampere. If the current is outward, going out of the plane, the compass needle will point in the same manner because the direction of magnetic field is same. So is there any effect? There is no effect. If we reverse the direction of the current, what will happen to that compass needle? It was pointing towards left hand side first. Now it will point towards. So if we reverse the direction of the current, the direction of the deflection will also be reversed. So compass needle will point in opposite direction. You can mention right or you can mention in opposite direction. The next part, figure 10.3 shows the view of a card from above of another vertical wire carrying current up through a horizontal card a centimeter grid is there, and point W is 1 centimeter. A centimeter grid is marked on the card, and point W is 1 centimeter vertically above the top of the surface of the card. What you have to do, the question is, state the magnetic field strength as S, T and W in terms of magnetic field strength at R. You use one of alternatives, weaker, same strength or stronger for each answer. When we compare the magnetic field of S with the magnetic field of R, what will be the magnetic field at S compared to R? The point S is closer to the magnet, closer to the wire. So if it is closer to the wire, it will be stronger. Then what about T? When we compare R with T, all are compared with, compare R and T with each other. From the wire you take the distance. So when you take the distance from the wire, both are 1 centimeter away from the wire, so that is why it is same strength. What about W? When we compare R with W, that is also same strength because W is also 1 centimeter or same distance as R. So these, because they have the same distance, so same strength, but S is closer, that's why it was having a stronger magnetic field. Okay, in this question, electromagnetic induction can be demonstrated using a solenoid. Solenoid means circular wire, a magnet, a sensitive ammeter, and connecting wires. In a space below, draw a label diagram of apparatus set up to demonstrate electromagnetic induction. Means how we can demonstrate electromagnetic induction, or how we can show that there is a change in magnetic field can induce EMF. So for that purpose, we should have a solenoid, a circular wire, connected to a sensitive ammeter, which can detect a reading, then a permanent magnet, and connecting wire. These are, because this part is a solenoid and the other part is a connecting wires and a magnet. It should be labeled like, you should write, this is a magnet, solenoid, sensitive ammeter, and these are the connection leads or connecting wires. Now the question is, State one way of using the apparatus to produce current. How I can produce a current from this apparatus? What I should do to produce a current from the apparatus which I drew here? I drew a solenoid, an ammeter, and a magnet. What I should do to produce a current? So by moving the magnet right or left, or by moving the magnet closer or away to the solenoid, or by moving the wire. So if I move the magnet, there is a change in magnetic field. Then explain why your method produces an induced EMF. So you have to basically write definition of electromagnetic induction. The movement of the magnet produce change in the magnetic field which induce EMF. So the change in the magnetic field, the movement of the magnet produce a change in the magnetic field which induces EMF. The next part, without changing the apparatus, I don't want to, we don't want to change the apparatus. We have a solenoid, we have an ammeter, and we have connection wires and magnet. Without changing this apparatus, what must be done to produce induced current in opposite direction to the original? So what I should do to produce a induced current but in opposite direction? So if initially I move the magnet towards the wire, so if initially I move the magnet towards the wire, then here answer should be move the magnet or move the wire in opposite direction from the to the original. If we want to produce a larger induced current, we want to produce greater EMF or voltage, what we should do to produce a larger induced EMF? So we should move the magnet faster. So the first one was the application of the Lenz's law, and the second one is application of Faraday's law. In the figure, 9.1 shows an apparatus used to investigate electromagnetic effect around a straight wire. You can see the two wires are there. Figure 9.2 is a view looking down, means you're looking from the top and looking at the paper down. A battery is connected to T1 and T2, so there is a current vertically down. So from T1 and T2, the current is vertically down, going down or into, down or into the paper. The question is, on figure 9.2, draw three magnetic field lines and indicate with an arrow to show a direction of these field lines. So because the current is down or into, so how we represent, we will use a right hand grip rule. So according to this right hand grip rule, my thumb should point in the direction of the current. Because the current is down here or into, if we are looking from the top, so current is into, so thumb is pointing into and fingers will turn around it. So these are the positions of the magnetic field lines. So Our thumb should point into and fingers will turn around. And we have to draw three field lines. So how to draw three field lines? First two field lines should be closer, and the third one will be, and this is the direction of the magnetic field. Using a variable resistor, the potential between T1 and T2 is gradually reduced. So we decrease the voltage. First we applied a higher voltage, now we reduce the voltage by using a variable resistor. State the effect, if any, that will have on the strength of a magnetic field. If we reduce the voltage, what happened to strength of the magnetic field? So it will also decrease. The strength of the magnetic field depends on how much voltage or current is passing. But what happened to the direction of the magnetic field? Is there any effect? So direction stays the same, it will have no effect. So direction of the magnetic field depends on how much current we have, what is the direction of the current, and the strength of the magnetic field depends on what is the voltage we apply to the source, from the source. The other part is there, but that's related to the force between the wires. Another rule is there for that. Figure 10.1 shows a cross section of a wire carrying a current into the plane of the paper. Figure 10.1 sketch a magnetic field due to a current. Detail of your sketch should suggest the variation of the strength of magnetic field and show the direction of field with an arrow. A current is into. So you can use the screen annotation to draw this, how the magnetic field pattern will appear. If the current is into, use a right hand grip rule. Your thumb should point in and your fingers will turn around. Yeah, that's right. So this is how the magnetic field pattern or magnetic field lines will appear. So first two field lines should be closer and the third one will be away, shows that the strength is decreasing. The next part is related to the force on the wire. Figure 10.1 shows a bar magnet suspended by a spring over a coil. The coil is connected to a sensitive zero center millivoltmeter. Zero center millivoltmeter means if the direction of the current changes, the direction of the deflection of this needle will also change. So in the question they mention the lower end of a magnet is pushed down. So we first push down the lower end into the upper end of a coil. So into the upper end of the coil, and it is held at rest. So it is stationary. During the movement, an EMF is induced in the coil. The meter shows a deflection to the right and then return to zero. Explain why this EMF is induced. So what is the reason why there is an induced EMF? Because there is a change in magnetic field, and due to the change in magnetic field there is induced EMF. And why the after some time it returned to zero? Because they mentioned we moved downward and then we held it stationary. So there's a change in a magnetic field as the magnet is moved, and the needle is deflected towards right hand side. The next part state what happened to the needle of a meter when a magnet is released from rest and it's pulled up by the spring. So initially we move the magnet downward and then we held it stationary, so needle is deflected towards right hand side. But what happened when we release this magnet? It was held stationary. When we release this magnet, it will go up. What we will observe? So if moving it downward, needle deflected towards right. So the needle will deflect to the left. In short, I am writing only left, but you will write the full answer. Now the magnet continue to oscillate. Oscillate means vibrate. The magnet continue to oscillate up and down, in and out of the coil. What we will observe on the meter? Like continuously the magnet is moving up and down. What we'll see on the meter? So the needle will also, no, we will continuously, because if a magnet is moving down, the needle will deflect towards right. When a magnet is going up, needle is deflected towards left. So it will be continuous vibration of the needle towards right and left, or to and fro motion of a needle as the magnet is moving continuously. It cannot produce a constant voltage. Why? Because to produce a constant voltage, there should be a constant change in the magnetic field, and with the same direction as well. In the same direction and constant change, that will be a constant voltage. But here the direction is changing, which produce a voltage in opposite directions. Electromagnetic induction may be demonstrated using a magnet, solenoid, and other necessary apparatus. What is meant by electromagnetic induction? The change in magnetic flux will induce EMF or current. In a space below, draw a label diagram of the apparatus set up so that electromagnetic induction can be demonstrated. So again, what we have to do, and it should be labeled: a solenoid, you can have a zero center voltmeter or ammeter, a magnet, describe how you would use apparatus to demonstrate electromagnetic induction. It's the same question. By moving the magnet, there will be a change in the magnetic field which induces EMF. State two ways of increasing the magnitude of induced EMF. So how I can increase the magnitude of induced EMF? Actually, there are three ways to increase the magnitude. Number one, move the magnet faster. That is one. Number two, use a stronger magnet. Even we move the magnet away, but it is at a higher speed, so induced EMF will be there, higher induced. So it depends on the change. Greater change will produce greater EMF. Move the magnet faster, use a stronger magnet, and use more turns for solenoid, or increase the number of. So if we use these things, it will produce a higher induced EMF. In figure 8.1, a magnet is moving towards one end of a solenoid connected to a sensitive zero center meter. During this movement, the current is induced in the solenoid. State three possible changes to the system that would increase the induced EMF. Again, the same question, how I can increase the induced EMF? So you will find a same pattern of a question related to this electromagnetic induction. A stronger magnetic field, or means stronger magnet, move the magnet faster, and by using more turns for a solenoid. Figure 9.1 shows a thin wire, a thin straight rod, basically X and Y, which is placed in a magnetic field between the poles. The wire from forms the end. X and Y are connected to a zero center voltmeter. So there is a wire. When X and Y are moved slowly upward, the needle of a voltmeter show a small deflection. State how X and Y must be moved to produce a large deflection in opposite direction. So how I can produce a greater deflection, number one, and then in opposite direction, number two. So how I can collectively change this movement? The wire is slowly move upward. So what I should do to the wire to produce a large deflection but in opposite direction? So moving it faster but downward. Because you have to write both in one sentence here. So larger deflection means move it faster. Opposite direction, first you was moving it upward. So move the wire downward at with greater speed. X and Y are now rotated about its central point. X raised and Y low. Explain why no deflection observed. What they're saying, X is move, like they're rotating now. X is going up, Y is going down. But the problem here, what we observe, we don't observe any voltage. What is the reason? Any idea? What could be a reason why we don't observe any voltage when X is raised and Y is lowered? There will be a change in magnetic field. When we are rotating, there is also a change in magnetic field. But they cancel out each other, because look what happened. X is going up. So example, if the current produced due to X is downward in this direction, Y is going down, so the current will be in opposite direction. So both will produce current in opposite direction, which cancel out each other. Is it clear? When we are moving X up, like X is going up and Y is coming down, it's a rotation. So due to movement of X, the current will be there in specific direction. Due to movement of Y, there is a current, but both currents are in opposite direction, so they cancel out each other. That is why the voltmeter reading will be 0. So X and Y both will produce current. which cancel out each other. Then the next part, it's related to oscilloscope CRO. Oscilloscope was there in the syllabus 2015 till 2015. It was a part, but not for 16 onwards. Describe an experiment to show how a magnet can be used to produce a current in a solenoid. Again, the same thing, same question. So you will have a solenoid, a voltmeter, a zero center voltmeter or ammeter, and a magnet. And it should be labeled. So you should label them magnet, coil, voltmeter or ammeter. And you have to describe experiment by moving the magnet towards or away. There is a change in magnetic field which induce EMF. Name the process that cause a potential difference or a voltage across a solenoid due to the movement of a nearby magnet. As the magnet is moved, there is a voltage produced. What we call this process? Electromagnetic induction. And when we produce a charge, that is called electrostatic induction. So in this question, figure 11.1 shows a solenoid connected to a zero voltmeter, zero center voltmeter, center zero voltmeter. A bar magnet is held with its north pole close to one end. The magnet is pushed into a solenoid and then brought to rest with its north pole just inside a solenoid. Describe the movement of the pointer of meter M. First we move the magnet towards it and then we stop. What we'll observe? So first we move the magnet towards and then we stop. The pointer will show a deflect, the pointer deflects and then return to zero or center. So deflection in the pointer and then stop. It's up to you. Even you can mention left or right because the meter, only the working of a meter based on practical deflections. So it is acceptable if you point out any direction or you just mention that there's a deflection in the pointer in one direction and then it will return to zero. The magnet is now pulled to the magnet is now pulled to the left of the solenoid at a higher speed than in the first part. Compare the movement of the pointer which is seen. Like now we are moving this magnet out but with a higher speed. What we will observe? So there will be a large deflection. It will move in opposite direction and it will have a higher deflection. That's right. It will return to zero. That depends on if it is outside the magnetic field, then it will return to zero. But the mark here is for mentioning that there is a deflection in opposite direction compared to the original, and then it will return to then there's a large deflection but in opposite direction. Return to zero depending on if the magnet if this solenoid is out of the magnetic field of the magnet, then it will return to zero. So simply large deflection but in opposite direction as the original one. So these are the questions related to electromagnetic induction. Because this is an important topic, you will find the same question every time repeated with the same concept. So that's why I discuss this topic with you. Any question related to the class? We'll continue magnetism next week as well. Any question or a doubt? Okay, so I'll end the session and share this with you.